Okay, right, so next thing we're going to have a look at is the flight orientation. Now this is great for birds, paper airplanes, anything that sort of has a direction to it and sort of looks like it's flying. And the module will deal with the sort of the roll and the pitch and all of those things based on the sort of turning and the velocity, which works really, really nicely. So I have here just my meshes spawning in a sphere, no initial random orientation. We don't really need that if we're going to use flight orientation. But if I add some linear velocity, so when we spawn, we fly over this direction, and then we're going to add an acceleration. And what I've done here, maybe I'll just create that again, just because it's not in the example. We're going to do an acceleration in Y, but I want it to kind of speed up over time. So if I change my input here to be a vector multiplied by a float, that's going to be my direction. In this case, that's the Y-axis. And the float, the value, is going to be driven by a curve. I'm just going to do a scale in and a value of something like 50, 200 maybe. So over time, the acceleration picks up and we get these to rotate round. Now, if I align these with velocity, and then rotate them, that does an okay job. We have a look, you can see they're pointing towards their direction of travel all the time, but there's no rotation, there's no banking. You'd have to go in and manually add that, but that's quite a tricky thing to do. All becomes quite difficult. So rather than do it that way, instead of using velocity alignment, if we use the flight alignment here, flight orientation, what that will do is as they rotate round, they will get some let's enable it, that's why it doesn't work. They will get some banking, and we can see that, which is quite nice. So we're not having to animate the roll as it goes round. We just say, right, this is the movement, and then the direction is all the rotations are all controlled by the direction and the module here. So we have options for how quickly it banks. It banks very slowly. Banking being the sort of the turn you get as you go around a corner. We have banking angle. If that's bigger, it's going to bank a lot more, possibly to the point where it's going over itself. It's probably not the thing we want to do. Let's go back to like a smaller amount. It's probably too high as well, and so on. And we can do speed up. So the decay rate, how quickly is it going to do its rotation, all of this kind of stuff. Very useful. We can set our mesh vectors. So in this case, well, I've rotated my model, so my point is now pointing in X. Same as before, if this was set to 0, my model is pointing the wrong direction. Now I can also change the direction here. So, oops, -1. So it depends what you want to do. I personally tend to find it's easier to set my upright and forward vectors here. Makes more sense, but we can also just rotate our model on our input as well. So lots of options and controls for rotations. It's probably the wrong way around now, isn't it? Nope. Well done. There we go. Yeah. As I say, there are 3 axes for an orientation, and it can be difficult to get them all right. But whichever you want to use, the orientation vectors here, or just rotating the model, it will work fine. You just have to keep adjusting it until it is correct. Okay, so that's the flight module. Does a very specific thing, but it does it very well. And say if we just had this velocity aligned, you'd get the turning around the corner, but you'd struggle to get, or you wouldn't automatically get that banking, which adds a lot to this, I think. So in the next module, or the next video, we'll have a look at rolling orientation. Okay, so the rolling orientation, this works great for spherical objects. So the first thing I'm going to do is just go in and turn my cone here into a sphere. And we kind of want to make sure that the sphere we're using has the origin in the center. It's going to use that to calculate. We could probably fudge it and do an offset in here and work it out that way, but much easier to make sure the pivot's in the right place. I think shape sphere, which maybe apparently doesn't exist. Okay, maybe I didn't bring it across from another project, but I think shape sphere has the pivot at the bottom, which is why we're not using it in this example. But there are other spheres we can use. And I believe we could probably just offset the pivot as well. Okay, sorry about that. Yes, as with all of these things, you can adjust things and get them to work, but it's also a lot easier just to have things imported correctly. So rather than dealing with a pivot offset in your sphere, just import the sphere with the model in the right place. Okay, so what does this do? Well, this uses a rotation. This creates a rotational update to your orientation based on the size of your model. And if let's just turn off the sample, maybe just spawn one of these things is probably fine. You can see it's actually pretty good. We get a pretty good representation of an object rolling along the ground. Which needs to be adjusted. Now there's nothing physics about this. It doesn't know where the ground plane is or what's happening. It's just a fake, but it works very well. Now there are settings for rotation rate, surface normal, things like that. How fast do you want to be rotating? And we do want to kind of, no, you might need to fudge this a little bit to get it to work. But yeah, just picks up the model, picks up the speed. Sorry about my dog, I'll just sort her out in a second. But yeah, really nice thing. If you're dealing with spherical objects rolling around, it kind of has to be a round object. If there's like a rock or something like that, there's going to be unevenness to it. It's going to struggle because it's not going to deal with the shape. But for a ball or something really spherical, it works quite well. We get this rotation. So again, apologies about the dog. I think it might be time for a walk. Okay, that's it for the mesh renderer. She knows she wants to go out. It's time to do something else. In the next videos, probably after a walk, we'll be doing the ribbon renderer. And hopefully there won't be quite so much barking, but we'll do that in the next video. Okay, right, so the next thing we're going to be having a look at is the ribbon renderer. So there are two different setups for ribbons in here. We'll start with this top one that's enabled. This is a spawn per unit trail ribbon, sort of ribbon. So this would be attached to another actor, and when the emitter moves, we're using spawn per unit, which we covered earlier, to spawn particles. And if I just turn only the sprite render on, we'll see that happening. So as I move my system, we're leaving these particles in the air. And what the ribbon renderer will do, will join these particles up. If I just create a new one, so using the default material here, it will just join those particles up. Just got the ribbon done, let's turn that off. Like so. Now it has some limitations. Ribbons are very good at what they do, but they unfortunately have quite a few issues as well. So you might see this as a bit stuttery and jerky. That's unfortunately because my spacing is quite high. So I don't get a particle until I've moved 50 units. And then as they die, they just kind of disappear. And we can fix that with a bit of scaling. So there's a module here, scale ribbon width, that will just animate the width of the particle or the width of the ribbon at that point, and that helps to kind of trail down to nothing, but it's still a little bit jerky. Unfortunately, if we have a high spacing, we get this kind of gap. If we have a low spacing, and let's just do particles every 5 units, we'll get a much smoother particle trail. But if I turn off the sprites now, Unfortunately, now we're able to do some other kind of errors. So here, if you do too tight a turn, you get a kind of triangulation error in the corner. And it's not really possible to have both things fixed at once. So depending on what you're making, ribbons might be great. There's certain things that you could only really do with ribbons, but it works much nicer on nice smooth motions like this, where there's not huge changes in direction and speed all the time. If this is sort of player controlled or driven by animation, it can quite easily get these kind of errors in them. So they're sort of starring around the corners and that kind of stuff. So as I say, there are some definite limitations to ribbons. Okay. Within the ribbon renderer, well, let's have a look here in the initialized particles bit first. We have an option for facing. So if we want to have our, well, we want to have an option for width first. That just makes sense. That's just how wide our ribbon is. So very wide is going to be a very different thing. And we can really see those kind of triangulation and yeah, edging errors now. Nice smooth movements, not a problem, but as soon as we get these kind of little jerky movements, it looks terrible. So let's try not to do that. Let's use a nice thin ribbon. Thin ribbons almost always work better than thick ones because of that issue. You can still do it, little movements, but yeah, not quite so easy to do. Facing mode, so if we change that to direct set and also in the renderer set the facing mode to be custom, now it will be facing a certain direction. So same as with the sprite alignment. So our ribbon now is aligned with the world and the Z up. So in this axis we can see it's wide, but obviously from the side here I'm not seeing anything, or not seeing very much. Twists works with the other ribbon renderers, which we'll get to later on, which is the other option here in the ribbon attributes. Okay, quickly moving on to how a ribbon renders. It has two UV sets. If I change this back to the Niagara debug material, let me just get rid of the width as well and turn that scale off. What will happen, oh, let's fix the facing as well, put the facing back to screen. There we go. What will happen with the sort of default settings is it will spawn the ribbon and it will scale the texture all the way along it. So the UVs go from tip to tail, width, side to side, and that can be useful. If you've got a very consistently moving sort of size and shape, then your texturing can work. But if it's something that stretches and sort of intermittently moves faster and slower, you can see we're getting some really bad texture stretching here. So useful for doing kind of a gradient from top to tail from full length. We said we could scale out the size of the trail at the end. That's fine. We could also just use a texture gradient that would help to mask out the last part of the trail. But that's not the only way to work here. There's also two other sets of UVs we can do. And so if I go to UV0 here, so non-uniform scale by total length, that's what we have now. So it's stretching depending on what we're doing. We can also do tiled by segment length. And if I just move this over here, what this will do will tile our texture depending on how many or how long our trail is. So as I move this faster, it gets longer. You can see we get 5 or 6 or even like 7 or 8. But as I move slowly, we're just having like 1.5. Really slowly down to like 1. And we just choose how long that tile length is here. So now it's going to tile over 50 units. And you can see we get that tile there. Pretty nice, pretty useful. If this was some sort of animated noise along the length of our trail, this would be done using this kind of method probably. And then the last one is the tiled by distance. Now this is what they call train tracks in the tooltip. Basically it's the same idea, but rather than being attached to the system, they're kind of tiling and just staying tiled in the world. And you see there's no animation in the texture here, it's just tiled. It's not attached to the, it's not based around where the system currently is, it's just where it spawns, which is useful as well. So tiled by segment length, you can see that kind of follows along, a bit like a flag or a banner. Quite useful. Tiled by distance. I can grab the right thing. Nope. That's now kind of like spawning into the world. And obviously these UVs can be used for an animated texture or whatever we want, and tiled and scaled and things within the material as well. Okay, that seems like a good introduction to ribbons and what they do. As I say, if you turn on a sprite renderer, that will debug and show you where the particles are that you're spawning. Not missed. So in this case, we're spawning a lot of particles. If we just quickly go into wireframe mode, you can see just how much geometry we're spawning here. And you can kind of see where they get these triangulation errors as well. So the more particles you have, the smoother the curve, but the more likely you are to get triangulation errors. The fewer the particles, the more the curve's going to kind of naturally curve out and things, but you have to have this this initial gap to deal with, and also the popping of the trail as the particles die. One thing to note, you don't really ever want to use a random lifetime on a trail particle. If I do something like 0.5 and 2, it uses the number of the particles as they're spawned as the connection between the different parts of the trail in the wireframe. So as this kind of scales up, as they start dying in different places, it has this weird effect. Maybe it's something you might want to use, I don't know, for a horror game, some unnatural motion. It's almost a bit creepy. But a very common thing when you've worked with other particles, you just put a random lifetime in, because 9 times out of 10 or 99 times out of 100, you want to have a random lifetime, but then when you're using it to spawn a trail from, you don't, because then it does this weird thing where particles die in the middle of the trail where the other trail is still alive. So just something to be aware of, making sure that you've got a fixed lifetime for your particles. Okay, in the next video we'll have a look at some of the other settings that we can do with ribbon shapes. Okay, so next thing we're going to look at with ribbons is the shape mode. So by default, a screen facing plane, we will get a nice trail, whichever way we want to UV it, and the various settings we already talked about in the last video. But we now have options for different shapes. Now if I change this to, for example, multiplane, I'm going to get a warning. So a camera facing multiplane won't look any different. So you can kind of see it's kind of a crossed plane, but if we change this to custom facing, now we're able to see this a lot better. So it's crossed planes, very useful if you have you want to fake a tube, or you want to fake the illusion of something with a little bit more 3D-ness to it. You can do camera facing, but you can also do crossed planes, and you can control how many planes to have. Obviously, the more geometry you have, the more expensive it gets. But now I've got this sort of, 4 planes, so it's like an 8-pointed star. And that's going to work nicely with the material if it's got kind of like a fade and maybe a Fresnel and that kind of thing, when we move around in a sort of more 3D fashion. Now this is where the initialize twist comes in. So ribbon twist mode, this is what angle to twist by. If I do a direct set, if I do a random value, I can spell random between, let's say, -1 and 1. As I move this along, it's going to give me different twists for every particle. So you could make a spiral or a twirl, that kind of thing. If you wanted to have it always increasing, you can use let's just try this on the fly. Let's do a multiply float by, I think it's int actually. Particle ID attributes, particles .id index, I believe. So this will be a a number for the particle. Might need to have persistent IDs enabled. Let's try it first. Oh, it's not doing anything. There we go. So the persistent IDs being on, and then in here, initialize particle, I'm using, it's bigger, return particle ID attributes, particle ID.index. You can read that in your own time and find out a bit more about this. But basically, we want a increasing number for every particle. So now we're multiplying by, let's just do a quarter turn. Each particle is going to be a quarter turn further, because as the number goes up, the rotation goes up, and we should get a nice uniform twist. Okay. Looks like it might be a bit higher. Not going to work. So I think there's a problem where it goes over 360. So it's twist, 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 and then it's twisting back. So it's doing the nearest thing. Rotations are complicated, unfortunately, and you can see as that sort of tessellation is happening as well. So something to investigate about how you would do a twisting ribbon. But what you can do is just some random values. So in here, ribbon twist. If I just do a random value from 0 to 1, we'll get a nice amount of twisting and kind of just breaking up that shape. The more planes you have, the more expensive in terms of geometry. And if you're doing a lot of planes to try and sort of simulate a tube or a round shape, there is also a tube option instead. So set to 3 subdivisions, it's sort of a triangular shape. You can see that. Obviously this can be up as high as you need. And we get our tube renderer there. Looking at the wireframe for this, it's relatively dense, especially when it kind of has to tessellate this. So as the kind of like the curvature of the shape, the higher the curvature, the more you need. And you do get these errors with twisting. Again, dealing with rotations can be tricky every so often as you go, especially up and down. The rotation changes from sort of this axis to this axis, and the point you're moving along is fine, but the point that's the other axis changes. So your kind of like forward axis is the same, and then occasionally it goes from upwards to downwards, and then you get this sort of full 360 twist, which won't happen on a nice straight line. But if you do like a big zigzag, I think it should happen on the big zigzag. Up and down, there we go. You can see it happening in the wireframe. Areas where the twist happens. So maybe accurate geometry. I'll try that. I wonder if I use smaller numbers. Yeah, ribbons, very powerful. Lots of things they can do. Can do some really cool effects with them, but they also have some pretty severe limitations, and there's lots of times when unfortunately there's an issue and you can't fix it. If I turn off tessellation, that may be going to fix my tube issue. No, oh, you're always going to get that twist. Maybe it's camera facing. Let's have a look at that as well. Let me show a camera facing, screen facing ribbon. Are you going to give me some errors as well? No, that looks better. So yeah, changing the settings, you can sometimes find something that's going to work. So by being screen facing our ribbon, we are always seeing the same part of it, but we're not getting that twisting happening. At least not in that axis. Make a cool snake. So yeah, that's ribbons. At least that's one of the setups for ribbons. That's using the spawn per unit setup. The UVs controlled however you like, 3 options, and you have options for both UV0 and UV1. So you can have one set to sort of segment length and one set to non-uniform scale or whatever it is, and so it's up to you. And you can do that twice, so you can have two different ones, and you can then choose your profile shape and the various settings that go with that, including sort of the width and the twist and the facing. But just do be aware that it's very easy for ribbon renderers to fail, and unfortunately not great because of the dynamic tessellation level, or dynamic way that it creates geometry. Unfortunately, sometimes it will just create geometry on top of each other, which doesn't tend to look very good. Okay, in the next video we'll talk about the other type of setup, which is going to be spawning particles from other particles and creating ribbons that way instead. Okay, right, just had a quick engine crash, so apologies if my setup's not exactly the same as yours if you've been following along, but it's a good time to move on to the next thing anyway. And what we're going to do now is we're going to spawn ribbons from other particles. So rather than being attached to a system and then attached onto another actor and doing trails that way, we're going to spawn particles and then spawn ribbons on those particles. So if I just enable the omnidirectional burst, this is one of the engine templates, I believe. Omnidirectional burst, there it is. And it's just a burst of sprites firing out in every direction, covering things we've already used. So sphere location, velocity from point, nothing particularly exciting in here. One thing to note though, we do have persistent IDs on. Oh, my UI is the wrong size. Okay. We do have persistent IDs on, so this is a requirement for this this approach to work. And if I turn on the ribbon renderer, what should happen is we get a nice trail along every particle. And so we're just going to do a quick demo of how that's set up. So there's two modules here: spawn particles from other emitter and sample particles from other emitter. If I just delete them both and turn on spawn per unit, and disable this. This is the same setup as above, so we're using a spawn per unit. Everything else is the same. The ribbon settings, we're not adding any changes there. The ribbon width in this case is scaling up and then down. Maybe that makes more sense. But as I move this around, we'll see we get a trail. It's very thin, but that's fine. We want something thin when we've got so many particles. But there's no extra settings from what we saw in the previous videos. So what we do want to do though is a spawn, not per unit, but spawn particles from other emitter. So this is the one we glossed over earlier, and we're going to use it here now. And we need to tell it, well, we need to add a sample particles from other emitter module. So we'll click fix, and that will add the other one for us. And then we need to tell it which emitter to refer back to. So if I turn this one on, and then type in here omnidirectional burst, and it auto corrects that for us. Now this is giving us a result. It's more like a kind of coil of rope or something like that though, because there's some settings we need to change. So what this is doing is it's spawning 10 particles for every one of the particles here, but it's using all of those particles as the ribbon. So the whole thing's kind of going round and round and round in circles. So if this just spawned one, that wouldn't be a problem, because now all the other particles being spawned here are correct. And if I just add a sprite renderer so we can see them, there you are. Obviously the spawn rate, controlling how many particles are spawning. But we do want to have more particles in our burst here, and we don't want everything to loop. So what do? Well, in our sample particles from other emitter, there is a lot of settings here, there's lots of information we can get, and we'll be covering this more in the next module, to the advanced concepts module. But what we can do here, if we just go down right to the bottom, particle ID ribbon sampling and particle ID distance traveled. So particle ID sampling, if we change this to apply sampled ID as ribbon ID. So effectively now we're saying each of the particle numbers here, which are persistent, it's going to be our kind of source for then doing multiple ribbons. And we get a trail per particle. If we also apply to attribute the ribbon UV distance, that will now work correctly with the ribbon UVs. So if I turn this bright render off here, you can now see our UVs are working correctly. Let's just make this wider, since we're only using a few of them. So there we are. Nice simple way of spawning particles that trail other particles. All we do is refer back to that first particle with our spawn. How many do we want? Do we want to cap that number, etc. And we just have to type in the value in it or the name, and it will also correct or autocomplete for us. And then finally, what are we sampling? Well, we'll go through more of the sampling here, but basically all of these bits of information we can get from this particle system and then use it in this particle system. So how old the particle is, what lifetime, what color, all of this stuff. So you could very easily build up a system where you had kind of like a hot purple glowing flying sprite and then a trail behind it, and that knew to be purple and it knew to be certain size and everything built on the link between these two. So do check that out and try have a go with that. The important one though is the particle ID sampling. If this is not used, we'll get all of our particles in a big trail. Could be useful. You can make some kind of like lasso type effect maybe. I don't know, some big rope. It's a bit interesting, although it's not really what we want. But if we have this enabled, now each one of the particles here has a unique trail here. Cool. That's it for the ribbon renderer. There are a few more settings, things to do with sorting and tessellation and things like that, but we've covered the important ones. It's not something I use that often because of the limitations, but as I say, there are certain things that you can't really do without ribbons. So yeah, good to know about, good to use where you can. In the next videos, we will have a look at some of the other renderers. There are a few others: beams, decals, lights, components, geometry cache, and then, well, 3D fluids, but we're not going to be using 3D fluids. But we'll just have a quick touch on what these are, what they do, and some of the settings that use to control them. Okay, so in the next few videos, we're going to have a look at some of the other renderers and the settings and controls we have for those as well. So not as much detail in these, but just nice to know about what there is available to us and what we can do with them. So here we are with beams. Our beam is a special type of ribbon. So the ribbons we already looked at were designed to be either attached to another actor or spawning ribbons from a particle, which is great. But sometimes you just want to sort of create a ribbon between point A and point B. And so we're still using the ribbon renderer. So all of the settings and everything that comes with the ribbon renderer that we just looked at are all still true. But we're also having this extra setup. So we're using a spawn burst, tell us how many particles to have. And then we need to have this one here, beam emitter setup. And what we're doing, if I just create a sprite renderer and add this on, disable the ribbon renderer for a second, maybe make my sprites a bit bigger. We're just spawning particles in a line. So we're just saying between point A and point B, I want to spawn particles. And that's what the beam emitter setup node does for us. So default is 100 units in X. Let's just make this a little bit longer. And we can specify these positions in absolute world space or in local space or any of the kind of spaces that we want, however we need. And we can also use tangents as well. So it's a bit weird, this one. If I turn on tangents, you can see we get a curve to our shape. And then we have the ribbon on it. But the inputs here, the tangents, they have an input, but it looks like it might be an old one. The multiply float vector by float, there's no data here, or there's no inputs for the data here, but we can just overwrite it by itself effectively, and you can see the input changes to a new dynamic input. So the way this works is we specify the vector for the tangent and then also the scale. So if I did the tangent as purely up, that's now curving that way. And if I scale that to 0, it's going to be a straight line. 1, 0.5, 0.2, 0.5. So you've got sort of a Bezier curve type control to this thing. Same with the end tangent. Let's do that as well. Vector by float 0, 0, 1.5. There we go. That should now be a nice flat straight curve of particles. Let's turn this bounce off again. That's bounce. There we go. And there it is. So one thing to note, this is doing it in E absolute beam end as well. Let's have a look. Well, curving off, if I don't use absolute values, okay, maybe just turn my tangents off. My tangents are probably causing problems. Maybe I need to be absolute tangents as well. Yes, I mean, you can see the problem we're having, the difference between world space and local space. If I make this all local space, does that fix things? That looks like it might. Yeah, it's very easy when working in different coordinate systems to think you're doing one thing and find you're actually doing another. There we go. Now if I put my beam tangents, yes. And there we are. We can create a curve. Which is what I'm trying to do here. So, takeaways to this. If we want to spawn a sort of static thing, we can specify a beam start and beam end, make sure we're using the right coordinate systems, and then use tangents if we want to curve them. And then all we then do, spawn burst our particles. How many do we want? The more we have, the smoother the curve. Even with quite a few, it's going to do a very small amount. It's still going to do a decent curve there. And we have another module here, beam width. Now it's worth noting the curve index for this is set to the ribbon link order. So when we're using the beam setup, should be writing the ribbon link order. Well, let's debug it and find out. It happens somewhere. So particle attributes, ribbon link order, spawn beam. There we are. So the spawn beam module is required to set up this value, and then the beam width value will read the ribbon link order, and we can then control our kind of shape of our beam. So we can have a nice smooth curve, we can have a point at one end, things like that. I turn off this bright window, you can see a bit easier. So there, it's flat at this end and pointed at the other, because that's what we have in our curve. And if I swap that round, flat and points move to the end, shaped, all these things, and we can make it wider, all of these things to control our beam. Twist's going to work with different ribbon shapes again. If I make this tube, well, it's multi-planed and custom facing. Looks pretty 3D. So if we look at that end there, you can see it's actually quite twisted. But all the same settings apply as before. Okay, one last thing with beams. We can make them dynamic. If you wanted to attach it to a point in the world that was moving, you could plug in a different setting every frame. And so if we just take this beam end, I'm just going to do a quick lerp. And lerp between, let's say, 500 and minus 500 in X, based on the normalized loop age of my emitter. That's not doing anything, but if I add the module update beam, it will now animate. And so you can recalculate your beam settings every frame if you wish, and you can create an animated beam, which is quite nice if you wanted to do sort of a, I don't know, a tractor beam or lightning effect, that kind of thing. You can sort of plug it in and point it at the right thing. Cool, that's beams. Basically ribbons in terms of all the rendering and settings and controls we have for ribbons, but a different way of working in terms of setup. You specify a start point and an end point in the beam setup, and tangents if you wish, and then spawn beam, beam width, and update beam if you want it to be live and work at real time. Okay, next video we will look at the decal renderer. Okay, so the next renderer on our list is the decal renderer. If I just disable and enable that. This is pretty simple. It uses a decal material. So if we're doing something like a bullet impact, something like that, where we want to have a material using decal blend mode, we can do that. Much easier than it used to be. Used to be you have to use a blueprint to spawn a decal at the same time and manage that together. Decal renderer just takes in the decal material directly, and then you can specify size and scale and things like that through the setup. So initial decal orientation. Which way do we want to orient? If you're doing a hit result, that will be sort of driven by the system, and the system will probably be pointing away from the surface and the normal, and so you probably want to use the direction along the surface. And yeah, quite a simple module to use. Set the material and the parameters. So decal size, decal size. Okay, so a few things. Yeah, sprite size, that's not going to do anything because it's not a sprite. In fact, none of these are going to do anything because it's a specific thing, a decal renderer. But we can see what the bindings are here. So decal size. So if I go to spawn, set new or existing parameter directly, decal size. And we can see it in the world here. Obviously no ground plane here, so nothing to be seen. If we select that warning, that's what that warning is saying. Will not show in the any preview scene. Please add a ground plane. We could add geometry in here, but it's much easier just to see it in the world. But there we are. So if I go decal size, let's in fact do a float, effective and float, 50, 150, 250, 50, etc. So whatever settings you want to control in your decal. So we have orientation, size, fade, etc., color. We can do that by creating a parameter that controls that. Initial decal orientation. Update decal orientation. So you can create a decal that will be rotate or interact if you want. Cool. That's the decal renderer. Most of the information is going to be coming from looks like a mistake. It's going to be coming from the decal material itself, but you can control the size and scale and orientation here from Niagara, and it just makes it a bit more convenient if you're doing something like a bullet impact. You want to fire out sparks and smoke and that kind of thing, and then probably a decal or decal, depending on how you want to pronounce it. Okay, in the next one we'll have a look at the light renderer. So the light renderer is a very simplified light. So particle lighting, it's too expensive to have a light per particle, even in the modern days of Lumen and everything. And so we tend not to do that. It's very expensive. And in fact, the light that we're getting here, the light renderer, is a very cheap toned down light. One thing to note, I have here disabled the inverse squared fall off. This is the natural kind of way of working. An inverse squared fall off gives us, well, it gives us a more realistic result, but it gives us a very expensive light. And so maybe I can show that a little bit better just with a normal point light, because the same thing applies here. If I create a point light, the fall off of the light and the light radius. So my light radius is this big. This is the number of pixels that are being affected by that light. If I go to the light complexity view mode, you can see that there's a cost. All of these pixels are paying the cost of this light, which is a large radius for not a very large area of impact. We can see the light here in the reflection, but there's not really any light spawning up here. If we turn off inverse squared fall off, we're then able to control the fall off of the light manually. So if I put the fall off down here, and if I do a fall off of say 0.1 or 0.00001, it won't go to exactly 0. You can see here at the edge, we're getting a very hard edge between where the light is and where the light isn't. And so the effect of the light, or the visual impact of your light, is much higher for your cost by using a light with a lower fall off. And generally in games, we're making approximations to get things to work at real time. If you're dealing with cinematics and you want something to be perfectly cinematic, then you can use inverse squared fall off. And it will give you a better, more realistic approach to how light physics energy, or light energy actually sort of like dissipates in the real world. But because of that, it becomes much more expensive. Small point light here, yes, it's in the reflection, but all these pixels paying the cost. If I turn off inverse squared, it's going to bloom out massively because the scale of the intensities want to be very different. I can have a much lower intensity light with a much lower fall off. This floor is very reflective, which is maybe making this not the most clearest thing to see, but hopefully you can see in the wall there how much that light is now affecting things. So as long as your fall off set to at least 1, it will always fade out to black at the edge. But something about 1 or 2 works quite nicely, and you can see that light having an effect. If maybe I make it a little bit more, by a little bit I mean entirely 100% red, you can see that effect. So up to you how you want to work with your lights. Inverse squared fall off is realistic, but is a large cost for your light in terms of the pixel cost of the radius that it's affecting. Personally, I think a smaller radius light with a sort of unnatural or artificial non-inverse squared fall off gives you more bang for your buck. And lighting and particles very often very expensive things. So that's what this option does. I almost always turn it off. And yeah, same idea as before though. So we're using the particle position. We can have settings for effect translucency. We can scale the light by the size of the particle, but it's also using the particle size here. So he says, I think. So the particle, oh no, it's maybe not. So the radius scale, so I can see that on my other screen. I can maybe show you exactly as well. So the radius scale here is controlling the size, but it must be coming a radius scale from somewhere. So the radius binding is from light radius. Aha. Yes, so we can see in the bindings where that parameter, or what parameter we want for that. I don't believe there is any kind of light setup modules. So instead we have to do that manually. So a set new or an existing parameters directly, and then you can see here light radius, light exponent. That's what the bindings are: light radius, light exponent. And I can control the fall off of my light as well. So very hard edge to 0.1. Value of 1 will fade to nothing. Maybe a little bit too artificial even for me. Value of 2 or possibly even 4. Give us a nice kind of bang for our buck in terms of radius and performance costs. We have inverse squared fall off though. We now need a much higher brightness. Brightness coming from particle color. What's happened here? Particle color, there we go. And you can see how we need, what's that, 1,000 times the intensity to get something visually similar. But yeah, performance wise, I think a non-inverse squared fall off light with a smaller exponent works better. But that's the light renderer. It is a very simplified light. It has no shadows. It is purely just sort of an optimized thing designed for cheap particles. One thing, just adding a light renderer to a particle sometimes isn't enough. What do I mean by that? So the settings in here for the sprite need to be a certain thing. If you were making, say, a cinematic and you wanted to have a little light on every ember in a fire, you would probably find that it would be difficult to control that. You wouldn't want to have the same settings for the embers as you would for the lights, and so there's some issues with that as well. So quite often what you would have is a single emitter that just controlled the light with the light renderer, and then that would kind of be in the center of the fire, and that's the sort of more optimal way of working rather than trying to attach a light to something else. Because if it looks like a fire flame, yes, it should have a light, but then if it does have different settings, and hopefully you understand what I mean. So yeah, cool. light renderer. As I say, expensive. Probably better off faking it with other ways, with more controls. But it's there. It does exist. It is possibly useful in some circumstances. If you want to control things, inverse squared fall off is a big thing. Look at that. The color settings, but all the bindings here, the parameters for these don't necessarily exist, but we can just create them. Or rather, they do exist. Once you add the light renderer, they'll be created, but we can set those values and expose them. So for example, light radius, we just create a parameter called light radius. It will appear in the list now. Phi2 light, so light enabled light volumetric scattering. Okay, if we did want to do a point light, there is a different kind of renderer we can use, and that is the next renderer we have here, what's called a component renderer. And we'll talk about that in the next video. Okay, so the light renderer, the component renderer. What the component renderer does is allows us to render absolutely anything from Unreal. All of these things are components. Anything that lives inside an object will be a component. This is the way Unreal system is built up. So for example, if I just create something even as simple as a static mesh, let's have a sphere, that'll do. Any shape will do. Let's have it bring it in the world so I can see it. Static mesh is an empty actor with a static mesh component in it. And that's what a static mesh actor is. It's the actor class with a static mesh component. And we can add more components. We can add a light to this or whatever, etc. And that's how blueprints are built up. That's how we build complicated things. It's like a kind of toolbox of different things. All done by components, and the component renderer will allow us to render any of those things through Niagara. Just delete that one. And so I can tell it what to have. We can do audio, we can do collisions, chaos. I mean, a lot of these wouldn't make any sense. Decal component, that would be the same as the decal renderer above. Static mesh component, that would be just a mesh renderer. But what we can do is things like point light, where this would actually make sense. Skeletal mesh, if you wanted an animation. As it says in the tooltip here, this is very new, it's very experimental, and it is not optimized for performance or safety. So be careful what you're doing with this if you are doing something with it. Something like the light though, we can do point light component enabled. Component count limit. Well, I'm only doing a single spawn burst of 1 here, so I'm very, very constrained. I don't want to do anything crazy. But now we have the full component settings, so I can change my light color, my radius. I can do things like cast shadows, etc. And so your particle component. Let's try not to crash this. There, and you can see you've got a point light component on top of your particle, but that will move the light around. And if I create a shape again, let's have a, I don't know, cube this time, should be able to see that this is casting shadows like so. So you can do a shadow casting light from Niagara. It just comes with heavy caveats in that it is a unoptimized and experimental feature. Using this thing here, the component renderer. Obviously the data here can't be driven by Niagara. So it can be driven by Niagara, so we can take our sort of settings and plug them in. So if I wanted to do, let's say let's do the source radius. No, let's do cast shadows. Let's say I want this to be a 50% likelihood of casting shadows. There's no binding parameters there, but on spawn, if I do set new or existing parameter directly, and we'll do a boolean that will be a random boolean, and then that now can be, well, let's give it a name, let's just call it bool, that's terrible. Random cast shadow. Can just about spell that. And now this can be hooked in, so random cast shadows. So if I restart my emitter, sometimes shadow is there and sometimes it's not. So you can control everything in your component renderer through the Niagara system, which is very, very powerful. But as I say, just do be careful. It is expensive and might be buggy and might not work. This is what happens when we're dealing with experimental new features. Okay. In the next one, we'll have a look at the geometry cache renderer very quickly. That's the component renderer. Okay, geometry cache renderer. It says it here in my note. Similarly, this is not designed for real time. What is a geometry cache? What does it mean? How does it work? Well, if we're dealing with non-real time applications, so Unreal being used in motion pictures, animation, architecture visualization, those kinds of things, or even just animating cinematics that then export to video and are rendered back, pre-rendered. So pre-rendered cutscenes, that's the kind of the word I'm looking for. In those situations, we can use geometry caches. Now, this is a way of exporting animation. So generally, if you wanted to do this animation in Unreal, you'd use a skeletal mesh. You would create a bone, you would skin that mesh to that bone, and then you would animate that bone. And that's how games animation and real-time animation has been done for a long time. It's very powerful, works very well. You're just updating one bone and then all the vert positions because of it. With the geometry cache, basically you're saving out a different file for every model, for every frame, and then it's importing and it's exporting. That's my understanding. It's obviously a huge amount of data, but it means you can do things like fluid simulations, and you don't have to try and transfer that skinning, do any kind of bone rigs or something for that. It's quite difficult or almost impossible to do. And so what we can do is we can just say, right, this is the mesh on this frame, this is the mesh on this frame, this is the mesh on this frame, and that's geometry cache. They are powerful. They're used in animation, feature film production, but they would be, I wonder if it tells you how big this thing is. It does not. But they would be not really suitable for most real-time applications. And so not something I've used. I tend to only do real-time stuff, or do a lot of real-time stuff, predominantly real-time stuff. There we are. And again, it is also an experimental feature. So since Unreal started being able to import alembics, which are another file format, a bit like FBX or OBJ, etc., you can export a geometry cache to an alembic and import that, and you can use that just as an animation, and we can also use that within Niagara as well. So that's what this does. As I say, I never used it. I would stay away from them for real time, but I don't think there's a lot of settings really to control. You export, do all the animation work offline, then import it, and then it just kind of plays it back. So, and then finally we have the Grid Gas Master 3D. This is a volume renderer for 3D gases or 3D real-time fluids. I will not be going into this in this course. There are some courses on real-time fluids in Niagara available. Go and check them out elsewhere. It's not something I've had a chance to play in with yet. I will be doing some Grid 2D stuff at a future date, so watch out for that. But for now, just know that there is other things here. So the volume renderer here, this is the way of rendering 3D fluids in the volume stuff. So, okay, quick overview of these. I say beams, ribbons between 2 points. They can be dynamic, they can be static. You can control the width and color and all that kind of stuff. Decal renderer useful for things like bullet impacts and scorch marks and burns, stuff like that. Used to be we'd just spawn a decal at the same time, so you'd have a bullet impact, you'd spawn a decal and a particle, and you'd have to control them both. It's just a bit more convenient to keep it inside of Niagara. Lights are lightweight, keep lightweight, light renderer, good for glows, that kind of stuff. Personally, I would probably have a separate emitter just for lights and have it nice and controlled, and try and keep as few as possible, because they do have quite a high cost. Even with the lightweight optimized version, they're still not cheap. But if you want really high quality light, then you're going to use a component renderer to get high quality light with things like shadows, but that comes with even more cost. And then the geometry cache and master, or the geometry cache and volume renderer, which we aren't going to go into too much detail with. Okay, that's our other renderers. Last few bits, we're going to talk about animation and then sort of materials and things like that. So sort of rounding out the deep dive here into all the modules. Okay, so let's talk a little bit about animation within particles. So we've covered this already in the initial setup and just throughout. Basically, everything can be animated. We've seen how Niagara has this sort of dynamic input system, and so you can take any property and just say, well, I want that to be driven by a curve. And we can do vector curves, and we can do float from curve, and we can do vector from float from curve, and so on and so forth. And it's what creates this such a powerful system in Niagara, because anything you want to do, you just have to think out how, and you probably can. So if you want one thing to be controlling another, or animating based on this thing and that thing, and all of that works. So let's have a look at some of the basics. First things first, generally we want to work with a kind of two-step process. To do the particle spawn, we're going to create values, and we're going to do randomness, and we're going to do an initial set. And then in the update, we're going to multiply and scale those things. So there is ways of directly controlling things in animation, but it's much easier or much better, in my opinion, to start with a random range and then scale that random range. And so you get kind of more variation and control over that. But both sort of workflows are equally valid. So yeah. So for example, here we'll talk about color. So the color is currently being set to just pure white. And we have a module here called color. This is a color curve over time. So this is in update. If I make my particles red and then blue, I can do that. And the bottom here is my opacity. To where they're full opacity and where they start to fade out. It's a bit laggy to work with, unfortunately. I don't really use this module, I'll be honest. But you can see here we have our different colors. So let's get rid of that white pin. And they start blue and they end red, and there we are. So you can just use a color curve. It will directly set the particle color, which is great, it's fine, but not exactly how I would work. I would tend to use an initial color and then scale color. And so if we ever look at the initial color first, so far we've looked at other things. So we've got direct set, so it'll just be white. I mean, you can make it red, etc. We can do a random range, so let's do a random color between red and blue. And now we have reds and blues and purples and everything in between. We can also do a random hue saturation value, and so we can do, in this case, starting with red and then hue shift by a certain amount, and so you can kind of have a base color and variation to that, which is quite nice. With all of these things, we can then want to use the scale color node. So scale color will take the input of the initial color. If we have a look at the parameter reads particles initial color. So whatever's set in spawn gets this tag of namespace modifier, that's what it's called. So initial, so this is what's set at the end of the spawn kind of script, as it were. And we're just scaling those values. So whatever's been set in here is now being multiplied and scaled here. And we can do things like, oh, that's size, not color. And so we can scale our color more in red, or just brighter in all colors, that kind of thing. And we can obviously scale our alpha as well, so scaling our curve out. Unfortunately, these two nodes together don't work, because the color here isn't writing to the initial color. It's reading the initial color. So the color here is being set. So although color and scale color feel like they should be two things that work together, they don't, because what the color node does is set the color parameter, and what the scale color node does is read the initial color parameter. So just something to be aware of. Took me a while to debug that one when it wasn't working before, because it feels like something that should be so logical and so sensible. Obviously, we could change the scale color node to affect the current color, but then what happens is it kind of scales and scales itself, and you get that sort of almost acceleration type thing where if you're, let's say, doubling the color at the start of your curve, well, the first frame it'll double, the next frame it'll double again and double again and double again, and you get this kind of exponential curve. So that's why this uses the initial color, because this is a sort of fixed known value by a multiplier. But yeah, there's something to be aware of. Cool. Size scale, we talked about this, size over life. Obviously we have the debug curves, or template curves, which are quite nice. We can create our own. So you can create a curve asset just as a curve on the content browser. Right click. They are in miscellaneous, I believe, curve. So if we make a float curve, if there was a very particular type of animation you wanted, or animation curve you wanted, you could save it out as an asset and then just import it, which works. Drop off. These are obviously the template ones. Very useful way of working. I usually have a couple of additional ones. Things like a soft fade's great, but I tend to pull this a bit further forwards and save that out as a curve. It's not quite that one. It's not quite that one. It's somewhere in the middle, like that. But obviously that's also quite a quick fix to do as well, so up to you. Note that our curve editors, these animation curves, don't have to be sampled by normalize age. So here we're using sprite size. We're going to animate a curve, and the x-axis, that's what this sort of uniform curve index, it's not very well named, but it basically refers to what does the x-axis refer to. Now for an animation, it's particle normalized age. We talked about that way back in the first examples. If we have a randomized age here, some particles live half a second, some particles live for a whole second. Well, we need the animation to reflect that, and so we use what's called normalized age. So 0 is always at spawn, 1 is always at death. Regardless of the length of the lifetime, it's always 0 to 1. Nice, makes sense. But we can also use these curves as ways of creating variation in our, as a sort of lookup table, as it were. So for example, here in my initialized particle, I have a size curve. So my sprite attributes, closed it down, oops, here we are. Let's reset this to default. So normally the size of a sprite, uniform, we talked about before, uniform, non-uniform, etc. But what happens if I want to have a distribution of sizes? So I want to have mostly small particles and then occasionally big ones. Well, I can do that. If I do a float from curve, the default is particle normalized age, but in Spawn, normalized age doesn't mean anything. And so instead, what we can do is we can use, what can we use? We can use particle parameter. Let me just undo, find out what it is we use. Brain's just gone blank. Just a random value. Of course it is. Yes, that makes perfect sense. Let's try this again. So we can use a curve. It's hard to think and talk at the same time. We can just use a curve. Yes, what we want to do is when the particle is spawned, we want to pick a random point along here. So if we did this, it's effectively just doing a random value between 0 and 1. But if I take my template, if I set this to say, well, mostly point to low values, and then this can be high values. We'll add another key and we'll bring that down here. Something like that. Does that work? Remember, we can export our curves if we want to see a bit more clearly. This scale on the side is really not very useful. And then if we scale this by, like, say 50, maybe turn off my scale sprite size. So what I'm looking for is particles. Well, not doing anything because I've not set the sampling. So if we just sample a random value between 0 and 1, so 0 here, 1 here, most of the time we're getting a value sometime around 0.1, 0.2, and then occasionally we get a bigger value. And so we're able to use the curve to really not do negatives. Let's change the tangents. Remember, you can right click or you can use the keyboard shortcuts to change the tangents. So I can break that tangent there. And I can do something like this. And effectively we're drawing a distribution. Let's turn snap off. And there we are. And so we get mostly small particles. So every particle spawns, picks a random value, and then looks up that value in the curve. And so we can create this kind of like intermittent size and scale, which is a very powerful way of working. Okay. Other option, let's talk about that. we can do animation in our particle spawn based on our emitter lifetime. And so here, if I do my scale curve, let's do another curve. And this time, rather than being the particle normalized age, we'll do the emitter normalized age, normalized loop age. And so our emitter is looping over, in this case, 5 seconds. And what we're going to do is at the start of 5 seconds, our scale is going to be, I'm going to keep this between 0 and 1 and use the multiplier. So the scale at the start of the 5 seconds is 50, and at the end of 5 seconds is going to be, let's say, 250. So as that 5 second loop goes round, you can see we get the intermittent sizes from this lookup table, and then also scales and changes in sizes from the emitter loop. And so again, we're building up this kind of multiple layers of variation, which will combine. And obviously this is just a straight line curve. We could do something like this would go up and then come down. So if this was maybe a, I don't know, water spraying out of a pipe, sometimes you're going to get big splashes, sometimes small splashes, all those kinds of things. And we can kind of combine that together with these kinds of curves. So as I've said in the end here, basically everything can be animated. It's a very powerful system because of that. You can use one animation to drive another animation. You can nest animations inside each other. All of that works very well. Generally, we don't need to do that level of detail. We can just go in and animate a few properties. But as always with particles, you're often trying to replicate dynamic real-world phenomena, such as fire and water, that have infinite levels of complexity. And so the tools we're using are very good at repetition. We're always using the same textures. We're always using the same sprites, the same kind of thing. So anywhere we can add some randomness and some animation really helps to break that up. And so just something like a simple curve, in this case in, I don't know, size or in scale based on the emitter loop, we can get some really kind of complex and dynamic effects where, although it's repetitive and cohesive, it's not too repetitive. It's not always the same, which is quite nice. Okay, I've rambled on about animation for enough parts time here. Last couple of things we're going to look at are materials and actually what information we can get out of Niagara and into the materials system. Okay, so looking at the last two examples here, we are going to talk about materials. Now we're not going to dive too deep into particle materials themselves. I have an entire course available on materials. Everything that we cover in that course is applicable to part materials. There's nothing special about particle materials. They are just a normal material on a piece of mesh. That mesh might be a sprite or it might be a mesh particle. The only slight difference is how we can transfer data between Niagara and the material system, and that's what we're going to talk about in the next couple of videos. So here in materials, I have a very simple kind of setup of a sort of cloud and a radial gradient that gets bigger and smaller. And the first thing we're going to look at actually is the material itself. Now there's a few nodes in here that are useful, we're going to use. One is the particle color node. So we've talked about color within particles. We can set it and initialize, we can scale it, we can do whatever we want to control it. And what that actually controls is this node here. So if this didn't exist or it wasn't connected, then we wouldn't see the different colors of the particles, and just everything up until now has been using this node. So this gives us RGBA data, so color and an alpha channel, generally used as color and an alpha channel, but they can just be anything. We could make a panner and we could use the green color as the multiplier of time to do kind of like a speed. Oops, that's not, it says time, that says time. That would all be fine. At the end of the day, they're just data, doesn't matter what the numbers used to control, it just is a way of passing information between the two. So let's say we were using a textured sprite that had a sort of imported texture on it. It didn't worry about color, it didn't need to be dynamically colored. We might still want to use the alpha to fade in and out, but we could use the other channels to control other things, and that would be fine. That said, there is a better way to do that, and that is with using what's called a dynamic parameters. So the dynamic parameter node is just created. It will come in with everything called param 1, 2, 3, 4, and we can rename them here. And since the latest versions of Niagara, we're able now to have 4 times a dynamic parameter. So this is stored as RGBA. You can see we have the 4 parameters. That used to be the limit, but if I make a second one here, I can set the parameter index to be 1. And now I can have param 5, param 6, param 7, and param 8, etc. And you can do this again and again and again and again. So obviously the limitation in Cascade was I don't know why I need to do this. We've started. There we are. I will finish. So this is now index 2. This will be index 3. And that will be parameters 13, 14, 15, and 16. There we go. So the limitation used to be 4. And so I have got used to building materials that don't use more than 4, and I'll be honest, it's not very often you start needing more than 5 and so on. But they are available to you there. So you specify the name, the parameter index, and they give you which of the 16 parameters that you can pass data. So there's those 16 plus those 4, so there's a total of 20 channels of data that we can pass from Niagara into materials, which is a lot. As I say, never really use more than 4, but there we are. Okay, so that's the material side of things. Particle color takes all the color information. Dynamic parameter takes the dynamic parameters. And the way we use that in Niagara is very simple. So we have a color modules. All of the color stuff has been built in so far. So color mode, if we change that to direct set and we make this red, you can see the color is updating. If I unpick that and just use a normal color parameter, and let's say make this white, like so, obviously now it's not going to do anything because well, actually it is because of the emissive. Let's not do that. Now the color here is completely being driven by material parameters inside the material. No matter what I do here, I'm not going to change any color. Obviously what's controlling things has to be hooked up correctly, but that's how particle color works. No, don't do that, do that. Go. Okay, so in this case we have our color, and I also have a dynamic parameter called emissive boost, and I want to do that for my emissive. So if I want to make this glow, in my particle spawn I can have dynamic parameters, and you can tell it what you want to edit. And so let me just edit the emissive boost. And I can make this bigger, I can blow it out completely, I can scale it to 0, I can do a random value. Now every time it resets, it's going to be brighter or darker, brighter or less dark, brighter or less bright, I suppose I should say. We could do a curve, float from curve based on the emitter loop age, emitter normalized loop age, and so now it's going to be, as this emitter goes over its 5-second loop, we're going to have a large value, then it's going to come down, although it's not because it's in spawn, so that's not going to work. So as always, the dichotomy of spawn versus update, anything we want to animate needs to happen in update. So if I put that back to being a random value, let's do a random value between 0 and 5. Now if I wanted to do a animation, here we are. Let's not do parameter 9. So we can choose which parameter set we want to write to by the checkbox here, and we can choose which parameters we want to write to by the checkboxes here. And so if I were to, example, take the emissive boost, I could do a curve, and this could be the curve for the lifetime of the particle itself, or it could be, yeah, again on the emitter loop age, this kind of thing. And now it's going to loop where it's slowly getting less bright until it fades away to nothing. So that's dynamic parameters. They can be edited in the update, so you can use them to create randomization. So you can edit it in spawn to create randomization. You can be edited in update to create animation. Random in spawn or animate in update. Don't know why that's written twice. There we go. We can also promote them to user parameters. So if we want to have a item of data that we want to edit here in the world on my parameter, my actor, I can do that. In this case, it's not doing anything because the update is set wrong. There we are. So if I enable scroll speed here, oh, I have an error. What's my error? Static rebel is not set to consistent value, so my value is being edited in both places. Let's just disable that. There we go. So emissive boost, sorry, it's not doing emissive boost. Let's do scroll speed. Scroll speed is now been promoted to a user parameter. We've seen these before. Obviously I can set the default here for how slow and fast and things I want things to be, but I can also now do that at this level as well. So we're just kind of passing data through. I'll make a second one of these. I can have one that moves really fast and one that moves really slow. And it's very easy to pass data through our Niagara system into our dynamic parameter, into our material, and then it works a bit like a custom primitive data, if you know about them from materials. Okay, so a couple of key things. First, anything we want our material to do, we have to pre-program into the material, whether that's from particle color or one of the up to 4 dynamic parameter nodes. Once we've done that, we just need to control it in Niagara, and here we can do it in spawn to create randomization, in update to create animation, or we can promote it to user parameters and make it editable here in the world as well. Okay, in the last video in this rather lengthy section, we're going to look at auto particle materials, and so yeah, data directly gathered without being passed through, and we'll have a look at that in the next video. Okay, so last video in this section, automatic particle materials. What do I mean by that? Well, we can see here we've got some different colors coming from our sprites. Over their lifetime they're changing, but we're not actually animating the color, we are animating the alpha. So where's this color coming from? They're spawning here as white, that's not what's happening. Well, let's have a look at the material. There are a load of material nodes that are very, very useful. They automatically pick up data from the particle system without having to be sort of programmed. So for example, if I right click particle, particle color, we saw that before, that makes sense, but we can also get direction. So in this case, the color of our particles is actually being driven by the direction they're moving in. That's maybe not that useful, but you can see hopefully how you could use direction to do other things within a system. So maybe we want some artificial fake lighting. So if the directional of the particle is moving towards the direction of the light, and use the sunlight vector, you could say, right, well then that will affect things and make them glow a bit more. And you could make these kind of, I don't know, shimmering type effects that happen based on vectors from the world and that kind of stuff. So access to the particle direction is really, really handy. Same particle position, where is it in the world? That can be useful. Radius, how big is it? Particle random, that's very nice. That's just a random value between 0 and 1 per particle. So every particle is spawned with a random value assigned to it that can be used by materials. Very good. Relative time, how old are you? So that's the sort of normalized age effectively. So from 0 to 1. Size in world, speed, rotation, sub-UV, all of this stuff. So you can get all of these items of data directly into your material. You can obviously pass this through as dynamic parameters and have more control over it. But if we just want a particle random, or let's say particle size, if you're doing something like little embers, big embers are going to be slightly brighter, smaller ones slightly less bright. We could connect that together in Niagara, or we could connect that together in materials. Doesn't really matter how we do that, but we have these options available to us. So a really nice set of nodes here. A little bit contrived here, but yeah, the bigger it is, the brighter it is. So just the maximum of the 2 dimensions, particle size being a 2D vector. So which is the bigger of the 2 dimensions. In this case, they're square, so they're the same, it doesn't matter. But basically saying, how big is my particle? Well, scale up by that and obviously I've put a scale factor in here to sort of deal with the emissive scale versus the size scale not being really the kind of same kind of numbers. Cool. So now if I wanted to change these, if I made the velocity faster, and let's do 2,500 and say 15,000, they're automatically brighter. And if I change my velocity from cone to, let's say, from point, now they're firing out in all different directions. And because of that direction, the color is different. And I can obviously still scale up the size of these things. So, yeah, visualizing the data with colors creates kind of like a sparkly firework effect, which is pretty cool. But yeah, the data is there. We can use it however we wish, rather than plugging in a particle parameter into a dynamic parameter to get the data into the material. I can just get it this way instead. So for example, dynamic parameter, well, dynamic parameters would be a little bit of a pain as well, because if we want to pass through a vector, we have to pass through it in 3 channels. But we can do a float from vector, and then the vector we want would be the particle, what am I trying to do here, direction. So particle velocity, and then we'll get the x-axis or the x component. We can just copy and paste this 3 times, and y and z, and this would work as well. So we could access the same data, and that's effectively what's happening. It's just doing it automatically rather than through a dynamic parameter system, which is a bit of a pain, as you can see. So don't use that. Instead, use this. Use these things as well. Used to be these only worked on GPU. Now they work on GPU and CPU. They're originally designed for GPU particles, I believe, but now obviously they work on CPU as well. So if I just change to GPU, you should see exactly the same, or thereabouts. Okay, right, that has been a bit of a marathon. Hopefully that's been sort of followable. Niagara is very, very powerful. There are a lot of modules, there's a lot of stuff we can do. Yeah, let's do an overview in the next video. Okay, yes, so a complete module breakdown, module by module, thematically. Hopefully it's not been too dry. Hopefully there's been some nice information. Ideally, you don't need to know all of this stuff all at once. Obviously that's not going to happen just from watching a quick video, but it gives you an idea about the stuff that there is available, and then you can kind of play with it yourself, have a tinker, or just refer back to these videos later on as sort of mini tutorials when you need them. I'll be honest, there are settings in here that I've never used. I've learned a lot just doing this myself, picking up some of the new modules or some kind of functionality that I never knew existed. So there is a huge amount of data. Don't feel like you need to memorize all of this, but just that idea and that concept. Fundamentally, particles are a few key things. There's the how many particles are we spawning, and like what's the rate? Is it a burst? Is it intermittent? Is it consistent? All of those kinds of things. Then we have the where are the particles spawning? Are they in a shape? Are they from a mesh? Are they I don't know, spawn per unit, that kind of thing. What are the other location modules? Refresh my memory. Yeah, is it from a grid? Is it from a shape? Is it from a mesh? All these kinds of things. And then how do they move? Are we just kind of controlling the velocities directly? In which case that's fine, no problem with that. But can be a little bit more tricky to do some realistic things than with that. Obviously much easier to use forces. We can just apply some gravity, apply some wind, apply some, I don't know, point attraction, that kind of thing, to create the movement that we want. And then what do they look like? So what's that? 4 things. How do we spawn them? Where do we spawn them? How do they move? And then what do they look like? And as long as those 4 things are working, you're going to build really nice and interactive or interesting particle systems. Went through the renderers, sprite renderer, mesh renderer, ribbon renderer. They're the 3 main ones, and then obviously the other renderers, so component, beam, decal, geometry, volume, much less used. And then looking at animation. I've run out of keyboard shortcuts for my cameras. Absolutely everything can be animated. Absolutely everything can be driven by data. And we'll see some of this in the worked examples in the final module. Yeah. Information passed through materials, information gathered from the world, all of these things can build up to really interesting, powerful, dynamic, awesome looking particle effects. As I say, hope that has been interesting, not too long and boring and dry. In the next module, we're going to look at some advanced concepts. So we're going to talk about collisions, we're going to talk about events, attribute reading, and things like Niagara parameter collections as well. So still lots more content, and then finally some worked examples as well. So we'll pick all that up in the next video.